In this video, we're going to find the sine and cosine of 45 degrees, or pi over 4 if we're working in radians. If you watched the videos where we found the sine and cosine of 30 degrees and the sine and cosine of 60 degrees, then you know the drill. Let's start by putting 45 degrees in standard position in a unit circle and recognize that the definition of sine and cosine tell us that the coordinates of this point that I'll label P on the circumference of the unit circle, specified by 45 degrees, has coordinates cosine of 45 degrees, comma sine of 45 degrees. All right. Now, based on how the coordinate system works, we know that since cosine of 45 degrees is the x-coordinate of point P, this distance here along the x-axis to take us over to point P must be cosine 45 degrees units long. And since sine of 45 degrees is the y-coordinate of point P, this vertical distance must be sine of 45 degrees units long. All right, great. So now we have a little right triangle that we can focus on in order to find the lengths of the red and pink sticks. So as we've done before, let's kind of ignore all the circle such stuff and just focus on the little triangle. So I'll come over here and paste a copy of that triangle into our document. And let's recognize that this other angle, this missing angle, has a measure. Well, let's find it real quick. Since we know that one of the angles is 45 degrees and another angle is 90 degrees, we know that we can add the missing angle to those two and get 180 degrees, since the sum of the angles in a triangle is always 180 degrees. Well, um, we know that these two here add up to 135, and 135 plus 45 more gives us 180. It's kind of easier to see when you look at it from the perspective of these two 45s add up to 90 plus one more 90 clearly gives us 180. So this 45-degree angle is up there. And when we step back and look at our triangle, we realize that what we have is an isosceles triangle, a triangle with two angles that are equal. And when two angles are equal in a triangle, the two sides opposite those angles must also be equal. So what we can go ahead and do is label those two sides with the same variable. So if we were to, for example, arbitrarily decide to call the red stick A, it means that the pink stick must also be of length A. They have to have the same length because the angles opposite those sides have the same measure, right? So 45 degrees is opposite A and the other 45 degrees is opposite A. Same angle is opposite the same side. Okay, well now what we can do is use the Pythagorean theorem to solve for angle A. Recall that the Pythagorean theorem tells us that the sum of the two shorter legs equals the square, I'm sorry, the sum of the squares of the two shorter legs equals the square of the longer leg. Why don't I just write it out? So a squared, the red stick squared, plus a squared, the pink stick squared, must equal 1 squared, the hypotenuse squared, the longest stick in the triangle. Well, now we can use this equation to solve for a. A squared plus a squared is 2a squared, and that equals 1 because 1 squared is 1. Now we can divide both sides by 2 and recognize that then a squared must equal 1 over 2. And now we can square root both sides of the equation. I've run out of room, so I'll navigate up here and start a new column. So if I square root a squared, I get a. If I square root 1/2, I get the square root of 1/2. And We can take the square root of a fraction by taking the square root of the top of the fraction. Square root of 1 is 1. And the square root of the bottom of the fraction, which is the square root of 2. And now we have solved for the side lengths of this little right triangle. And that number, it's might seem a bit odd because it's got a square root in the bottom, but there's nothing wrong with the number. We can use it without any problem. So we could go ahead and recognize that this length A, this value A, which was the length of that red stick, is 1 over square root of 2. And similarly, since that value is also the length of the pink stick must also be 1 over the square root of 2. Now, the truth is, though, that there are, it's often the case that people use a slightly different version of this number. There's kind of a avoidance of numbers that have square roots on the bottom due to historical reasons involving the way that approximations were done before handheld calculators. And so what people usually would do is multiply this by a kind of clever version of the number 1 to adjust the format of it. If you multiply this by square root of 2 over square root of 2, you don't change the value of the number, you just change kind of how it looks. And we'll see that in this case, the top, oh, I'm sorry, I didn't multiply by 1, did I? I want to multiply by square root of 2 over square root of 2. That must have been a little bit odd. Let me just start that over a little bit here, huh? So, in order to adjust the form of this number, we'll multiply by 1, and the version of 1 we'll choose to use is the square root of 2 divided by the square root of 2. All right, and then when we multiply these two fractions together, 1 times square root of 2 in the top is just square root of 2, and on the bottom, square root of 2 times square root of 2 is 2. So square root of 2 over 2 is another version of this number. Arguably, it's more commonly used, but there's really no reason to value one over versus the other. They're both perfectly legitimate numbers, and so we can use either one. In a sense, it's sort of like how zero point 0.5 is the same as 1/2. They're equal and they're both acceptable numbers. Um, okay, so finally, let's go ahead and draw our conclusions. Since these values we've just discovered are, whoops, these values we've just discovered are coordinates of this point, we know that the x coordinate of this point must be these red values, square root of 2 over 2, and the y coordinate of this point must be this pink value, square root of 2 over 2, the same value. The x and y values are the same. Somehow failed to erase that. And then finally, we can conclude that since cosine of 45 degrees is this x coordinate, we can conclude that the cosine of 45 degrees is square root of 2 over 2. And since sine of 45 degrees is the y coordinate, we can conclude that the sine of 45 degrees is square root of 2 over 2. So the sine and cosine of 45 degrees are exactly the same value. And of course, that ends up making sense when you think about how the 45-degree angle cuts right through the middle of the first quadrant. So the x and y values are the same. It's right along that line that has the same x and y values all the way along it. So we end up with the same sine and cosine values.